Our vision at ARMS is to help make our clients safe and successful by helping them make reliability a reality.
We're a specialist reliability organisation. It is all we do, and it's all we've been doing for over 2 decades. We use real data to drive effective decisions that connect reliability through to work execution to actual asset performance improvement. Innovation is at the core of our culture, and it's a continuous process. We're in a really unique position where we provide advisory services, and we provide technology, and we build capability in client organisations. So we get to continually evolve the application of reliability in industry. Making reliability a reality is a really timeless statement for us as well. It talks to our heritage, and it also talks to our future. And we really want to bring that to life for our customers. We really want them to get the results that we know are there, and we know we can help them deliver to improve their asset performance.
Hello. Hello. Welcome everyone to this session of MainTrain 2021. I'd like to thank our sponsors, ARMS Reliability. They're the sponsors for the session today. A few housekeeping tips just to follow. If you have any technical issues during the presentation, please open up the Q&A on the bottom of your screen, and our meeting host will be able to assist you. We have technical people in the background. You can find this feature at the bottom of the presentation window and feed loop. We will also be conducting a Q&A session after the presentation. You can click on the top corner of this window, of your video window, to create a larger presentation if you wish. And if you have any additional questions or comments after the presentation, feel free to reach out to the speaker to chat with them in the networking portion of your feed loops. Further ado, I'd like to welcome Errin Evans from ARMS Reliability. And today she's going to be talking about how using a reliability block diagrams help an oil facility expansion. Errin, over to you.
Thank you. Okay, is everyone able, are you able to see my screen pretty well? Okay. Excellent, thank you all. So to give you all an overview of the project I'll be sharing with you, I was working with an oil sands facility. They had the capacity to load and ship about 100K barrels a day per oil, and they were looking to increase that capacity by or to 120K barrels per day with the addition of a diluent recovery unit. And so the overall system's mean availability and capacity performance were of interest. So was the performance of the diluent recovery unit. There was a special emphasis and interest there. One interesting point was that the design choices were not finalized yet for their vapor recovery unit. And so what I did was multiple scenarios, simulating existing or using existing VRU packages as a basis. In those the details from those package performance details came from sister sites vapor recovery units. So the first pass diagram was built per the most recent process flow diagrams that were available. In one of the pre-conference presentations, one of my colleagues, Kent Knight, shared this tip in going into a facilitation, assume the model is wrong, just know that there are going to be things that need to be changed, but make your aim to give participants something to mark up. And so the major, if I were to say bad, using quotes, assumption is that all of the systems are required for the success path of the reliability block diagram. But I'll go into more depth in the next slides. The failure models themselves were used or were assigned using previous reliability block diagram studies with this client and from ARMS' library. And so the failure models within the software include, at a minimum, mean time between failure and mean time to repair. And those models were selected based on equipment type, the region, and the similar operating context. Model assignments were used as a starting point for that dialogue instead of being taken as the gospel. And then failure model and logic details were validated in those facilitation sessions with the client. So just to go over some basics of reliability block diagrams, and especially how the software that I was using views availability, we'll look at a simple series or a simple subsystem in series. And so availability is the measure of the likelihood that a system will be ready to operate when it's called upon to operate. And so that's right out of the Certified Reliability Engineer Handbook. And so for this simple subsystem, should blocks A, B, or C fail, the system fails or it becomes unavailable. And then availability decreases as the number of blocks with availability less than 100% increases. So then if we're looking at that same subsystem and we're approximating that system's availability just using those three simple blocks, then as that, you can see the impact as availability of blocks increases. And so in this example, I'm actually assuming that the three blocks share the same availability, even though that's usually not how things work. But we can see that even if we have, something we would consider great availability, like 95%, maybe it's great in your operating context. If your subsystem is performing, or if one of the blocks is performing at that 95% availability, the availability of your system is actually much lower. So it's actually 86%. And so oftentimes it's something that we have to keep in mind when we're looking to improve reliability, especially when there are a number, especially when it's essentially a simple subsystem with lots of blocks in series. So that's where redundancy can start to help us. To give you a little insight into the simulation software, Isograp's Availability Workbench Availability Simulation module, or AVSIM, is what was used for it. Availability, it's an availability simulation and system optimization tool. And it handles series and parallel systems. It's able to handle some pretty complex interdependencies pretty well. The simulation duration, all durations are in hours within the software. So 219,000 hours or 25 years, which is the desired life or the expected life for this facility. And then the number of simulations was 1,000, and that's really to bring down errors and anomalies and those sorts of things. It really helps to get as many simulations in as possible or as practical. So one really interesting point for me was, I mentioned before that or may not have mentioned yet, but we actually had a working relationship with this client. And so we've done a number of reliability block diagram engagements with their reliability team and their project team. And so there were some, from a stewardship standpoint, especially since at the end of this engagement, I was going to be handing this model over to the reliability engineering team for them to continue to steward it. I really needed to ensure that there was continuity between this build and previous builds. And so part of that continuity was utilizing the legend that had been previously established for block colors. And so you'll see some of those, you'll see some of the block colors in the examples that I have later on. But it actually gave me the capability of seeing where my buffers were, where capacity reductions, equipment that existed on multiple pages, any notes regarding the RBD logic, which you'll see in some of the examples that I have further on. And then also equipment that maybe during facilitation, there was equipment that showed on process flow diagrams that's actually being disposed or has already been decommissioned. And then the last one that was really helpful was that there was a specific color block for questions or assumptions that needed to be validated with their team. And one of the really helpful pieces, especially since there were so many different colors, as you guys see, is that the block labels and details, including the color, are searchable within the software. So here's an example of the simplified view of their system. If you notice, there's a plus sign for some of these. The plus sign in the top right corner is what indicates that there's a subsystem on the lower page. So I'm actually able to click into the software and drill down into pages of systems and subsystems. And so the availability of that system can be approximated if we were to multiply the availability of each one of those areas that you see listed. So now if we were to talk about some general assumptions that were made about this or going into this effort, we had steady state operation assumed. So in other words, no allowance was made for commissioning tasks. Repairable items exhibit the same failure or repair characteristics, irrespective of the number of times they repaired. So we know that that's not quite how things work in real life, but that's how it works within the model. And then there are even, as you get more detailed, there are even other ways that you can consider with those repairable items. But each repair returns the item to an as good as new condition after maintenance. The reliability block diagram was constructed from existing data, and then the comments were captured during facilitation sessions. So sometimes if there was a quick change that could be made, I would make it in the facilitation session. Sometimes if there were some other things that were maybe involved, I would actually take those offline before it was time to meet with the client again. And then collateral failure damage was not considered in the development of these failure models. So each failure model event is considered an isolated failure. It's easy to get sidetracked pretty quickly otherwise. So next we'll look into the build specific assumptions. So the first assumption was that assets will display an identical MTTF and MTTR to similar equipment types from sister sites within the same regions. There are pros and cons to this that I'll share later on. But where those similar types did not exist, ARMS' library and previous RAM studies were used and then reviewed with the client. And the key here is really working with them as a partner and providing clarity into how those assumptions are made. The pipeline is 100% available for feedstock, rail cars 100% available for export. And then individual instrumentation and valving were not considered, but I did include a block to represent spurious trips of critical instruments. And you all may have seen that actually in it was one of the first blocks that we saw here. So that's where the spurious instrument trips are represented. And then 6-month winter and summer phases were used to represent the warmer and cooler months. The software allows for rules to be defined based on these phases, and I'll share what some of those were later. And then lastly, emergency power, UPS systems, UCS systems, and labor resources were assumed 100% available. So now if we talk about the capacity assumptions, or some of the phase-specific, build-specific assumptions that were made, many of them were related to capacity changes for assets that are in parallel operation. And this is based on the warmer and cooler months. And so here's the breakdown of how those capacities are impacted depending on which phase we're in. And next, I'll talk through some of the constraints before we get into the scenarios and select logic and all of those things. So next, there were some constraints that were put in place to limit how the software allowed failures and PM activities, similarly to how plant turnarounds and short stops might be handled within a production facility. And so process cleaning activities is one of them. Those are constrained to months with a lower production impact because that's usually how the facility operates. Then cleaning activities were staggered amongst trains and redundant equipment. And so within the software, I actually staggered different activities so that, let's say, the software calls for one of the process cleaning activities to occur. If that train is out or out of service, then it won't call on the second train to be taken out of service. And then planned maintenance, very similar. So planned maintenance on redundant trains was constrained if the sister train was unavailable. So with that, I'm actually going to take you through to see some of the select logic details that were included. And so I mentioned that part of this project was actually making sure that what was turned over was something that could be stewarded by their reliability team. And so I looked at a number of different scenarios, or 3 specifically scenarios for their vapor recovery unit. And so part of what I did so that I could see how each one of them performed and was also available to keep them within the same model is I used select logic blocks. So these blocks are not actually subsystems, but I used them with either true or false logic to limit whether or not one system was considered as part of the success path. So even though these are in parallel operation here, they're not considered parallel paths. And so, and here's one of the notes that I left just to explain how to use it and how the logic was being used here. So in this case, the VRU scenario selection change blocks, the logic is true, so no success path unless the scenario is being run. So it's just as if these lines or these paths didn't exist at all within the model. But then if we were to drill down, I'm actually we'll pretend and we'll drill down into one of these scenarios so that you can see what it looks like when you drill down into one of these subsystems. And so here's an example of the scenario subsystem. I mentioned that there were, what I used as a basis for these scenarios were subsystems that existed at similar sites within very similar operating contexts and regional locations. And so here's an example of one of those scenarios. And so I have some notes here about which, and I recognize that it's tough to see all of those. It's really not so that you can see all of these details so much as seeing that there are 3 trains. I've broken down what the capacity is through each one of these lines, and then specific notes about the mean time to repair for the vessels, the pumps, the coolers, based on the data that the reliability team has been has been collecting and updating. So then if we look at the system overall, its overall performance, the profile above displays the system performance for the expected life of the facility expansion, with the mean availability in gray and the mean capacity in blue. The availability dips that we see, so we see these dips, these major dips here, those dips correspond to turnaround activities that they're performing. So the next thing that you've probably noticed is that the system capacity mimics that availability profile, but there are some dips here where we can see. And so those dips that we see are actually capacity restrictions from redundant trains. And so the system overall is available because because your success path is still there. So there's still a path, but there's a reduction in that capacity because you're not running through all of the redundant equipment that's provided. But what it demonstrates to us is that the redundancy that's in place, as well as the subsystem and operational bypasses, are effective in that the dips that we're seeing here are process cleaning activities that have to be performed, or actually they're all process cleaning activities, as well as some known failures or failure times. So if we look at the simulation results for key areas, the baseline scenario that was used was selecting one of the VRU packages as a basis and then using the other two for comparison. And so the mean availability out of the baseline was 92.58% mean availability at a mean capacity of 90.62%. The scenario 2, 93.19% mean availability against 91, or with the capacity, a mean capacity of 91.12%, and then slightly higher performance out of scenario 3 VRU package with 93.2% availability and 91.2% mean capacity. The diluent recovery unit, which was one of the areas of high importance because it's one of the ones being added, and they're also able to make some design changes as needed. The mean availability for that unit or that subsystem is 98.2% with a mean capacity of 96.89%. And so part of what they were able to see is that or I guess part of what it demonstrated for us was looking at seeing all of these key areas. You see where the highest impact to your availability and capacity can be made. So those are the key areas. But now I want to take you to see all of the areas all together. And remember, these are like our 5 blocks in, these are our 5 blocks in series. And so we see how the water treatment area, the boiler feed water, steam generation, diluent recovery, tankage, and VRU, and then utilities. So part of what we see what the mean availability of the terminal altogether is with that package, with that first VRU baseline, but we're also able to see that there aren't major bad actors in terms of subsystems. They're all performing fairly well, but once you start to line a number of systems and things up in a series, as soon as you start to take away from that 100% availability, you see the impact that it has on your overall availability. And so the water treatment area and diluent recovery units, so we see all the others are in the 99% mean availability. These areas, water treatment and diluent recovery, were in, or I guess we're lower comparatively speaking, but they also include many more assets, making a higher level of availability difficult, even with scheduled maintenance. The other outcomes out of the simulation were downtime importance rankings. And so those rankings are the availability losses ranked in terms of their hour contribution to system downtime. So anytime the success path was interrupted, there were process buffer blocks that were included in that ranking. And so one challenge is that their impact may actually hide the contribution of assets that those system bypasses are protecting. And so I'll actually show in the next slide, but one of the highest contributors was a system buffer or an operational bypass, because it allows for continued operation, but at a reduced capacity. And so to help myself understand what was really going on and can we explain it and what equipment is placing a demand on this buffer, I actually zoomed in on this system and its protected assets and ran the simulation in watch mode so that I could see where it was placing the demands on the buffer, what those which protected assets were failing without redundancy or with an extended repair time, so that I could give the client some meaningful results out of it. And so here's an example, or not an example, but here's the rankings for those downtime importance. And so just based on the magnitude of the impact of this buffer, you probably understand a little better why I spent some time watching to see what was happening and which ones were contributing. And so those, after reviewing which equipment was protected by the buffers, I was able to provide better recommendations to the client for where they may see the most impact of improvements or changes. So another outcome is actually the capacity importance rankings, and it's communicated or it's calculated in terms of percent capacity loss. And so additions to the top contributors were a tank that had an expected MTTF of 10 years and a mean time to repair of 2 weeks. And one of the benefits of talking through all of these things during a facilitation was actually understanding and the conversation around issues with entering the tank for maintenance and things that due to solids buildup, and then some of the design options that they were reviewing for changes to this tank system or even changing how they operated. And so those design choices would not eliminate capacity losses so much as ensure the repairs are held within those boundaries of how long they needed to take. And then 18-month process cleaning activities were the next, or also account for additional percent capacity losses. The simulation conclusion, the performance of the terminal with the expansion is a 92.58% mean availability at a mean capacity of 90.62%. The performance of the diluent recovery unit, one of the areas of interest, is a mean availability of 98.2% at a mean capacity of 96.89%. The simulation also confirms high or slightly higher performance is achievable with the selection of a VRU package that has a 3 by 50% configuration, similar to Plant 2 or Sister Plant 2. And then incremental increases in availability can be achieved with greater coordination of the process cleaning and maintenance tasks. So the recommendations to the client were to perform an RCM study of the highest capacity contributor equipment types to develop those cost-optimized strategies for these assets, consider design changes and or condition-based monitoring, which would allow secondary or mitigating actions to be performed during planned outages, perform a cost-benefit analysis to determine what design changes or recommendations to incorporate for those top contributors. So those percent loss hours, downtime, contribution values can then be used to weigh the equipment type and capital spending choices. and then update the RBD as needed to evaluate those design changes and potential capital spending. So I wanted to make sure that I shared with everyone some of the challenges and how we worked through those, because it wasn't all rainbows and sunshine. But one of the challenges that came out of the benefit of using previous failure models was that it could be helpful, but it could also be distracting for facilitation participants, just because there were so many options. And so part of what helped me was sending those assumptions ahead of time, because sometimes during facilitation, someone may ask, well, you know, why did we choose this one? This tank is really a better option. And you go down into the details, and it turns out that the failure model, the MTTF and MTTR are actually the same. So one of the other challenges was that the RE team members were not part of this project, but they were unofficial stakeholders as the stewards of the RBDs. And so part of what I did to help mitigate any challenges or any issues that could come up was meeting with them before kickoff to discuss whether or not there were any updates to models since turnover, and then developing logic within the RBD to allow all of the scenarios to reside within a single project instead of multiple files, and then including labels on the RBD pages which detailed any special logic or rules cases. So I showed you all that with the scenario select. And then the last challenge, which you can probably relate to, we had our kickoff meeting, and then there was a 6-week delay because most of the participants were in RCPHA and then had vacations planned. And so all of the facilitations were scheduled before the break just to make sure I got on people's calendars before they filled up. If you have any questions or any part of this work resonates with what you're doing or what you want to do, definitely, take a look at our website, or you're also free to shoot me an email. And with that, I'll turn things over for Q&A.
Well, thank you, Errin, for that presentation. We already have a few questions already. The first one is from Errin, and it is, what is the software application that you use to model this RBD? Does it take distributional models that are other than exponential distributions?
Okay, so it does. I was hoping someone would have this question. So it's the MTTF or MTBF versus kind of a Weibull approach to it. So the software that I use is Availability Workbench's ABSIM, or Availability Simulation Module, and that's what I use to do it. The reason that I chose, it does take other distributional models. I've actually done in the past a hybrid RCM study and RBD approach for a client who had a number of failure modes that they needed to consider, and they were actually able to talk through that failure behavior. If you're not sure about the failure behavior, there's probably not a need to go into, so far into other distributional models, because staying at the MTBF level allowed me to look at multiple failure modes within one, really looking at anything that took it out of the success path.
Okay. We have another one here from Tony. Tony is, how do you draw the boundaries around the system, a system/subsystem?
So it kind of depends. For me, it helped to start with the PFD boundaries that were there. So sometimes the PFDs may be on multiple pages, but you know that it's a specific subsystem. The other thing that I'm also very careful about when I'm doing an RBD is making sure that I don't get outside of the boundaries of what's in our control. And so, for example, maybe there's a need to look at external utilities or something like that. Maybe it is helpful, especially if there are issues, but we really can't, if I can't impact or if I don't have, I guess, influence into what the utility provider is doing, then I would draw my boundaries within what's within the scope of control.
Okay. Is there any more questions? Oh, we got another one here from David. And David would like to know, where do you usually get the MTTF data? From the equipment manufacturers or from the users or both?
So if I can, I prefer user MTBF data. In this case, a number of the MTBF assumptions came directly from previous RBDs with this client because they had very similar equipment types and very similar operating context. Part of what I do when I'm dealing with something specifically, I dealt with a client who had a number of equipment items that were bespoke equipment, so very unique to their operation, serial numbers 1 and 2 and 3 and 4. So the manufacturer, we can break it down into components, but it was really helpful to talk through those things with with the people who run the equipment and who operate it. Manufacturers usually give us data in terms of like your B10 life, and so that's really tough to. I'm always reluctant to use their data because it's lab data. It's outside of the operating context that we're using. So usually it's a mixture of information from the client, information from our library where we've done previous models on different similar equipment types or similar operating contexts, or sometimes engineering judgment. But the best part about it is that it's just the start. So you're always going in, you make those assumptions, and then you recognize that you're going to have to change some of those assumptions.
Okay. We have another one from Mohammed. Was running an RCM cost model for each subsystem considered in this model?
I'm not sure I understand exactly what the question is. So in this case, I did not do an FMEA or RCM cost model with them for these, although I have in the past facilitated an FMEA with a client and then converted it from the RCM cost module within So I've gone from RCM cost to ABSIM before with an FMEA, but it was a very special case. In this case, I just built within ABSIM.
Okay. We have another one from Mohammed. It says the RCM model within an AWB. That might have been part of.
I think he was providing clarity for
the other question.
He's familiar with the other module.
Okay. Is there any other questions? Any other questions? Oh, well, that seems okay. Well, thank you very much, Errin. Make sure, to stop by, and you can stop by the ARMS booth there in the exhibit hall, and you can ask if you have any questions later on, and feel free to meet up with Errin in the networking tab on your feed loop. Anything else is just thanks for everybody turning up, showing up, coming up. Oh, got another one from Tony. Just showed up. Can you comment on how the RBD model can relate to criticality?
I'm not sure I fully understand the question, but I guess what we can if I'm understanding correctly, so usually the way that the way I'd equate reliability block diagram to criticality, I look at it this way. The reliability block diagram is those equipment items that are actually important or critical to the success path for maintaining availability. So there may be some equipment that if it fails, there's no impact to whether or not you can produce your product. And so those items are usually not included as part of the reliability block diagram because it lets us really simplify it. So you might assume that the things that are included as part of that reliability block diagram are the items that are your higher criticality items, but that's not always the case. So I'm not sure whether or not I fully understood the question that you were asking, but okay.
Yep, great. Okay. Well, any other questions? We're just about out of time. A few minutes left.
Perfect. Thank you, Tony.
Oh, one last question here.
I agree. I definitely agree, Sean. You can definitely use it to help you identify the things that are higher risk. Because if something fails and there's no impact to your success path, unless it's safety critical, you're kind of hard pressed to argue that it needs to be high criticality.
And
so the Pareto chart that you saw was actually the ranking of downtime importance. It's one of the reports that spits out of the simulation.
And one other one from Tony. It's a success path. Tree was also on my mind.
Got it. Okay.
Well, I'd like to thank everybody. And we are just about out of time. Thank Errin again. And if you have any further questions, her contact info will be up for a few more minutes. And then feel free to network with her in the network tab. And remember to start by the ARMS reliability booth in the exhibit hall. Thanks. Stay safe. Bye.
Thank you so much, all. Goodbye.